Good morning. How's it going? Wonderful. Has anyone done the homework yet? Wasn't bad, right? Okay. Again, I would urge you guys to LaTeX it. It's a one-time investment of an hour or two learning how to do it. And again, it's really not bad. Literally all you have to do is go on Overleaf, overleaf.com or net, I can never remember, and put in the text file, the template that I've given you, and literally just fill out the areas and say, write the proof here. So it's a little bit of learning how to do some math type setting while you write the proofs, but that's it. It's a one-time investment that will pay off for the rest of your life. And when I was assigning it, I wasn't sure if I should make it due sort of class time on Friday like I usually do, but since I'm not collecting in person, you guys are uploading a PDF on Canvas, I figured I'd just make it due Friday midnight. So yeah, you don't have to have it done by class on Friday. If you do it Friday night, that's fine. Just get it done. So yeah, anyway, we'll pick up where we left off last time. We were talking about parallelograms, and we're actually done with parallelograms for now. We'll move on. We'll get to rhombuses in a second, but before we do that, we'll prove this more general statement about the following. It says if I have a line segment AB, so here's my line segment AB, and I want to look at the locus, this set of all points. I don't tend to use this sort of archaic language of locuses, but all locus is a set of all points that satisfy some properties. It's a curve, so a curve that satisfies the properties. So if we look at the set of all points that are equidistant from, why don't I say B and C? It's A and B. Equidistant from A and B. Then my claim is that that's the perpendicular bisector of AB. What's the perpendicular bisector? That's the line that cuts through AB, right down the middle, right? It's got to bisect this line, and it cuts through it perpendicularly. Right, so there is a midpoint of this line, and of course there's infinitely many lines that pass through that, but there's exactly one that cuts through it perpendicularly. That's the perpendicular bisector. And my claim is that that's the same as this. It's the same as a set of all points that are equidistant from A and B. Visually, not too hard to convince yourself, right? Let's say this midpoint is, what have I called it in my notes? X, actually. Let's say that midpoint there is X. Is that midpoint equidistant from A and B? Yeah, so it's on this curve we're looking at, it's on this locus. It's one of these sets of points, or it's in this set of points that's equidistant from A and B. But what else is? Well, go up just a little bit. Go up just a little bit. And if I measure these distances, that distance from this point to B and this point to A, that's pretty clearly still equidistant, right? Go up a little bit more, and a little bit more, and a little bit more. And if you're looking at this set of all points that are equidistant from A and B, you do get this straight line. You get this straight line that actually cuts through AB perpendicularly. So this is what we want to prove, that this perpendicular bisector is the exact same as this set of all points that are equidistant from A and B. So how do we prove this? Well, one way is sort of like proving the two sets are equal. How do you prove the two sets are equal? If I have a set A and a set B, well, usually you would say, I want to prove that A is a subset of B and B is a subset of A, and together, that implies that my two sets are the same. Right? This is a standard proof from 201, I think. Anytime you ever want to prove two sets are equal, you prove that they're subsets of each other. And if you think of lines as being sets of points, that's essentially what we're going to do here. I'm going to show that if you're on one of these lines, if you're on, say, this locus, this set of all points that are equidistant from A and B, then you must also be on the perpendicular bisector. And vice versa, if you're on the perpendicular bisector, then you must be on the set of all points that are equidistant. So that's more or less what our proof is going to look like. So proof. In fact, I don't really need this picture right now. Although I'm going to draw a picture somewhere, so maybe I will write my proof over here. But I will indicate exactly what we're going to do. So we want to show the following. We actually need to show two things. One is that every point on the perpendicular bisector is indeed equidistant from A and B. Okay, so if you're on this perpendicular bisector, then you're on this set of all points that are equidistant from A and B. And two, the opposite. If you're equidistant from A and B, you're on the perpendicular bisector. So 2 and 2, if a point is equidistant from A and B, then it is on the perpendicular bisector. And does the logic there make sense? So as long as we showed those two things, then we've shown that these two lines are actually the same. So let's see, let's break this into two pieces, right? It's essentially two different proofs. We need to prove both of these statements. So here's a proof of 1. We'll see if we can fit it on the board. Let's see. First I need to label some points. So let's let x be the midpoint, as we had before. Let x be the midpoint of the line segment AB. And let's just let P be some point on the perpendicular bisector. And let P be a point on the perpendicular bisector. A, B, here we have X right in the middle. Perpendicular bisector is just a line that cuts through perpendicularly through X. So there's P is a point on it. And you can extend this infinitely in both directions, but I'll just look at the relevant segments that I care about. Well, what can I do with this picture? We studied triangles a lot, and pretty clearly I can construct two triangles here, right? I've got, in fact, 3 if you want to think of it like this. I've got the whole big triangle, ABP, but what I'm actually going to think about is these two separate triangles here, AXP and BXP. Okay? So consider the two triangles AXP and BXP. Do I know anything about side lengths in this picture? Any angles? Anything? Yeah, so by definition of x, AX and BX are equal in length. What else?
90 degrees in the middle.
Yeah, so I've got 90 degrees right here. And these two triangles share this side, so they both have the same length on that side. Is that enough to say that these two triangles are congruent? Yeah, right, SAS. Two corresponding sides, two corresponding angles, two corresponding sides. So by SAS, they're congruent. Oh, well, let me write down the observations we just made. So we have AX equals BX by the definition of X. By the definition of X. PX equals PX. PX equals PX. And that angle AXP is equal to 90 degrees, which is also the same as angle BXP. So just writing down the details of what we just said, but therefore, by SAS, we have that these two triangles are congruent. So by SAS, triangle AXP is congruent to triangle BXP. So by identifying corresponding sides, that means that the hypotenuse of both of these right triangles, those are congruent. Same length. And that's what we wanted to show, right? Maybe I should have stated this right off the bat. The first thing we wanted to do is show that point P was equidistant from A and B, which we've done now, right? Length AP is the same as length BP. So we'll just finish this by saying, and it follows that AP equals BP. Which, if I had more space, I would write one more line on here, or just one more sort of clause, which is so P is equidistant from A and B. I'll tell you what, try part 2 on your own. I'll give you a few minutes to work on this or think about this. If you're equidistant from A and B, so pretty much you'll have the same picture, but with other bits of information given. So, and you don't necessarily have X right off the bat, but you would choose a point P that's equidistant from A and B. Try and somehow prove that P lives on the perpendicular bisector. Is there anyone here that wasn't here on Monday? I don't think so. Okay. And I'll point you in the right direction. What's true about this triangle in this picture? What type of triangle is it? isosceles, and we know some stuff about isosceles triangles. Moreover, we know some stuff about lines that connect to this point P, right? And so what I want to do here is I want to drop an altitude down from P. So I'd let X be the point on the segment AB, such that XP is an altitude. What's an altitude? Altitude is the line drawn so that it intersects the base perpendicularly. Alright, so let X be a point, in fact the point is a unique one. Let X be the point on AB so that XP is an altitude. I guess I'm saying and because there's technically three of them, but it's the unique altitude from vertex P. What I'd like to conclude is that this is a perpendicular bisector. Well, it cuts through it perpendicularly, I just need to conclude that X is actually the midpoint, right? That's what it means to be a perpendicular bisector, is it doesn't just cut through perpendicularly, it cuts through the midpoint. By construction of the altitude, it cuts through perpendicularly, but how can I conclude that X is the midpoint? I suppose at this point you could reprove this, but we've actually already shown that for isosceles triangles, medians, at least from the sort of peak vertex, medians and altitudes are the same thing. Right? So because what do I call this triangle? Sorry. ABP, because ABP is isosceles, we know that XP is also a median. Right? Or in other words, that is X is the midpoint of A and B, of AB. X is the midpoint of AB. And therefore, XP is perpendicular bisector of AB. And therefore, XP is the perpendicular, I don't know why I decided to write the whole word when I've been abbreviating it, is the perpendicular bisector. So what does that mean? Well, there's a unique line passing through P and X, and we've shown that that line is the perpendicular bisector. So if you're equidistant from A and B, then you live on the perpendicular bisector. And that's enough, we're done. Yes?
If we're doing problems like this in the future, would it be useful to say something along the lines of like, without loss of generality, choosing P, or is it clear enough in this example that since we're choosing P arbitrarily, it doesn't matter?
Yeah, I don't think here you would have to sort of state without loss of generality. Without loss of generality is usually sort of when you're given a set and you're just arbitrarily choosing one. I suppose here I'm not given a set that I start with. I have the whole plane and I just choose something. So yeah. Any other questions? All right, so anyway, we were doing this. This is sort of a technical point. The proof actually wasn't that easy, but we're doing this to prove something else back to quadrilaterals. I was almost tempted to call this not a theorem, but a lemma. A lemma usually being sort of a side little technical result that you use to prove something else. And then calling his next theorem a theorem. But I went with the way that the textbook handles it, which is they call this guy the theorem, and our next result follows almost immediately from it. Hence, it's a corollary. And the corollary is this. And this is really what we wanted to prove all along. That the diagonals of a rhombus, ABCD, I don't see any reason to give the rhombus a name here, but anyway, the diagonals of a rhombus ABCD are perpendicular. What's a rhombus? Anyone remember the definition? I'm sure you already knew it's a four-sided shape. All four sides are the same length. Right, so for example, a square is a rhombus, but not all rhombuses are squares. So all four equal sides. So for example, you can take these diamond-shaped things, although this looks more like a square that I've just turned on its side. But nope, don't like this either. We'll try one more time, and if it's still pretty terrible, we'll just go with it. Whatever. A, B, C, D. So what we want to show is that if you take these diagonals, then they cut through each other sort of mutually perpendicularly. That's what we want to show. That's the claim. So here's A, B, C, D again. And we'll just start off our proof by saying let A, B, C, D be a rhombus. Let A, B, C, D be a rhombus. And we'll state again exactly what that means. If ABCD is a rhombus, that means side AB is the same length as side BC, same length as side CD, and so on, right? So that is AB equals BC equals CD equals DA. So in particular, of this list of equalities here, that means that A is equidistant from B and D, right? A is equidistant from B and D. So by our previous result, again, the proof here should follow almost immediately from the previous result, hence the name corollary. And it should follow immediately from what we just did. A is equidistant from B and C, so it's on the perpendicular bisector of B, or sorry, perpendicular from B and D, so A is on the perpendicular bisector of BD. So because A is equidistant from B and D, it is on the perpendicular bisector of BD. What about C? Well, C is also equidistant from B and D, right? So similarly, so is C. So both of these points, A and C, those live on the perpendicular bisector, right? But there's a unique line that passes through 2 points. There's a unique line passing through A and C, and because there's only one line that contains both of them, that line containing both of them must be the perpendicular bisector, right? So this segment, I don't really want the whole thing here, or the infinite line, let's just go AC. That is the perpendicular bisector of BD. So, invoking some uniqueness stuff here. Since AC is the unique line, containing A and C, it must be the perpendicular bisector. Does that logic there make sense, right? There's only one line that contains both A and C. It's this line segment AC, and if they're both on the perpendicular bisector, then this line must be the perpendicular bisector. There's only one line that contains them both. Yeah, so we're done. That proves that these lines are perpendicular to each other. So hence, AC is perpendicular to BD. Done. I don't know how important rhombuses will be to us in this class. Parallelograms in this class and in Geometry 2 are super, super important. I don't think I've ever invoked rhombuses ever in Geometry 2. But we'll see where we use them here. One little bit more terminology. What's a rectangle? How would you define rectangles?
Parallelogram with opposite equal sides.
Parallelogram. All parallelograms have opposite equal sides. So
With all 90-degree angles.
all
Internal 90-degree angles.
all 90-degree angles. Yeah. So that would automatically make you a parallelogram. So it's enough just to say all four all four equal angles. And if all four angles are equal and they sum to 360, then of course this means 90 degrees each. So what's a square? A square, I guess one way to define a square would be it's a rhombus and a rectangle, right? So square would be your rhombus plus a rectangle. But of course you know these things, right? You know what rectangles and squares are, so I won't dwell on that. And that took way longer than I was expecting. I thought we might actually have a really short class today, just because I don't have much on area at all. I intend to give it a much quicker treatment than the textbook does. But we'll get through almost all of area in probably about 10-15 minutes here. See, our next section, 1E, is area. And here's a rectangle. It has base length B, and it has height H. So what's the area? Base times height, right? Area is base times height. So that's just BH. And we can take this as a definition if you want, right? So we'll just define, if you want, the area of a rectangle to be base times height. And our textbook always uses K, so I'll match them. K for area, capital K, is BH. What if I then move on to parallelograms? Alright, so here's a parallelogram. I'll say this side here is B, and this sort of height of the parallelogram is H. What's the area now? Well, it turns out if you know stuff about rectangles, you can pretty much immediately find a formula for area of a parallelogram by doing this little trick. Add in some stuff. Add in two triangles that will make you into a rectangle. Okay, so now I've got height H, and these distances here turn out to be equal. I'll call those two distances x. So sort of the base of these triangles we add. Alright, so what's the area of the shaded rectangle? Area of shaded rectangle, or not shaded, it's dashed. Area of the dashed rectangle equals what? Well, it's a rectangle, and we know the formula for an area of a rectangle. It's base. The base here would be b plus x. Right, so b plus x times the height, times h. Or just bh plus xh. What about the area of the two triangles? Area of two dashed triangles. And the trick here is I'm doing this without invoking a formula for the area of triangles, right? I'm assuming I only know how to find areas of rectangles. Well, one thing you could do is you could say I'll move these off, I'll cut these off, and then push them together, and I will get a rectangle, right? If I take both triangles and I push them together along their hypotenuses, I get a rectangle of height h and of base width x. Right? So there's a trick there. I'm not invoking any formulas about areas of triangles. I'm just observing that these are actually congruent. You can show they're congruent by SSS. So I can push them together like this, form a rectangle, and the area of those guys must just be xh. So the area of the parallelogram is the difference, right? We'll take the rectangle, subtract off those triangles, and we're left with the area of the parallelogram. Area of the parallelogram is BH plus XH minus XH. So we have this formula here as well for parallelograms. Area is base times the height. But notice the height isn't a side length, right? It's not a side length like it was for rectangles. It's sort of this altitude drawn from one of these vertices. Any questions? All right. So let's take this and do triangles, and we'll get the formulas you're familiar with, plus some more. Plus some more, but how about triangles? So here's a triangle. It looks too isosceles for me. In fact, it almost looks equilateral. Let's draw a slightly weirder triangle. So I've got this side as length b, and what I'm going to do is, again, I'm going to drop an altitude. Right, so I'm going to drop an altitude here. We'll dash it. And this altitude has length or height h. So I'm sure you already know this area of a triangle, 1/2 times base times height, right? 1/2 bh. But how can we demonstrate that? By the way, there's one more case that I'm not going to draw here. You can draw this, you can convince yourself of it though. But there is a case where maybe this top vertex lies way out here, and then my height is actually outside of the triangle. But all I'm going to do is I'm going to take a copy of this, and I'm going to by superposition, I'm going to flip it over and give you a copy of this triangle, sort of flipped over and living above. And now I have a parallelogram, right? So the area of the dashed parallelogram is twice the area of the triangle. Again, how do you really know that these two triangles I've drawn have the same area? Well, SSS on them, they're congruent. So it's twice the area of the triangle. And we already showed how to find the area of a parallelogram. It would be B times H. And that means the area of one triangle is half of that. One half BH. Oops. I wanted to call this K. Alright, so there's areas of triangles. And really not much that I have left here. We'll talk about the law of sines really quick and a few other formulas for areas for triangles. But let's see, I'm going to label a triangle in sort of an odd order for me. Here's a triangle I'm going to start over here. A, B, C. Okay. Here's my height, like always. Well, the way I'm labeling H in this picture, there's of course two other altitudes, but I'm going with this one. And what I'm going to do is I'm going to label the sides as well. Usually, if you have vertices like this, you label the opposite side with the same letter, but lowercase. That's one common labeling scheme. So there's A, B, and C. And you'll notice that the way I've labeled H here, the side I've called B matches up with my base earlier, right? B for base. Although, if I were to flip this, I could think of A as being the base, or C as being the base. So the formulas will look similar, but B doesn't technically refer to the base in the formulas I'm about to give you. It refers to the side opposite vertex B. So what do we have? What is sine of A? What is sine of A in terms of everything in this picture? Wait, do I want sine of A? Sine is, yeah, it is sine. Sine SOHCAHTOA is opposite over hypotenuse, right? So sine of A is H over C. And that means that H is C times sine of A. And so what's my area? Well, area, as we saw, is 1/2 times the base times the height, right? Here, my base just happens to also be called B. So it's going to be 1/2 B times H. So in this picture I've drawn, my base corresponds to the letter B. And that means that H, we've already found this, is 1/2 B C sine A. And similarly, you can go through, you can label the other altitudes and come up with other formulas for area in terms of two side lengths and an angle, and you'll get K is 1/2 AB, actually let's go AC sine B, and K is 1/2, what have we done? C, AB sine C. I tend to just remember these formulas by remembering that the two sides, the two letters not inside the sign, are the side lengths outside. All right, A, B, and C appear everywhere. So all three of these things are equal to K. Right? They're all the area, so they're all equal to each other. Right? This means that 1/2 BC sine A is equal to 1/2 AC sine B is equal to 1/2 AB sine C. And this is the famous law of sines. It's just not written in the form you're used to. So let's put it in the form you're used to. Multiply everything by 2. And divide everything by ABC. Right, and then we've got the famous law of sines. Sine A over A is equal to sine B over B is equal to sine C over C. So this is the famous law of sines. Or it might be more commonly given as a reciprocal of this. Sometimes it's A over sine A equals B over sine B, but to me they're the same. All right, so I just want to mention one more thing here. Just a recap of these triangle formulas. What do we have? We've got K is 1/2 BH. All right, so this is area given two pieces of data. Given one side length, the base, and an altitude. All right, so area from one side plus an altitude, the corresponding altitude. We've also got these other formulas that we just had. K is 1/2, for example, AB sine C, and friends, the two other versions of this, so plus others. This is area given two, or in fact three pieces of data, right? Two side lengths and an angle. So area from two sides and an angle. The question is it possible, I don't have quite enough space, so I'm going to finish this up here, unfortunately. Is it possible to come up with a formula for areas of triangles just using all three sides? And you should suspect immediately the answer should be yes. Why? Because if I know all three sides of a triangle, it's uniquely determined, right? SSS tells me there's exactly one triangle up to congruence with three given sides, which means its area should be fixed. So I'll bring this up here. There is a formula that we'll get to in the next chapter, something that might be new to you. The formula for area of a triangle given all three sides is the square root of S, I'll tell you what S is in a second, times S minus A, times S minus B, times S minus C. Where A, B, and C are three sides, as usual. So these are just three sides, area from three sides, A, B, and C. And S in this formula is what's called the semi-perimeter of the triangle. Semi-perimeter of the triangle is usually what it's called. The book actually has a typo here. They divide by twice for whatever reason. I'm pretty sure it's unintentional, it's a typo. Semi-perimeter is exactly what you think it is. What's the perimeter of a triangle? Side lengths A, B, and C. You just add up all three sides, right? A plus B plus C. Semi-perimeter is half of that. So the semi-perimeter is A plus B plus C over 2. Turns out in formulas involving triangles, this expression pops up so often that people decided, hey, let's give it a name. It's a semi-perimeter, and it'll make our formulas look better if we replace it with a single letter S. Okay? But this is what it is, and we'll prove this later on in chapter 2. And there might be a little bit more I want to say about area next class. I'm not sure. We might leave it alone, but we'll stop here. Thanks, guys. Have a good rest of your day.